as I recall, if I was to draw a timeline, the first thing that excited architects and engineers to use concrete was the realization that as you make stronger and stronger concrete, you can reduce the size of the columns at the bottom. If you were using, let's say, a 5,000 or 6,000 PSI strength concrete, which compared to today, we can easily go up to 12,000, 14,000, and even more, okay? You would wind up with buildings with humongous sizes of columns, right? So there was a motivation to start using high-strength concrete to compete with steel, because you can get the appropriate size columns that make the building work from a functional point of view and an architectural point of view. And then, because of that, there was this movement to try to get higher and higher strength concrete. And as we were discussing, if you go back many years ago, like in the 60s or so, an engineer, when he designed a building, he would design the concrete mix. So he would say, I want my concrete to have this percentage of sand, this percentage of aggregate, this percentage of cement, and any other additives he may want to put in it. As it became a science that enabled you to have really strong concrete, the manufacturers got in, okay, as Tom was mentioning before, and especially in Chicago. I remember someone asking me, how did you guys design such and such a concrete mix for a building we were working on in concrete? And we told them we haven't the slightest idea, because it became a big secret, right? But the engineer and architect on the project would say, performance specification of the concrete. I want it to be this strong, I want it to behave this way or that way. And then the manufacturers, okay, would develop the mix. And they kept those mixes close to their chests, all right? And Chicago was really a leader in that area. You can't say that too much in front of a lot of New Yorkers, but I'm a New Yorker, but you can tell that already. But Chicago really was. So that kind of started the whole thing, the strength of the concrete, keeping the column sizes down. But then we started realizing things that we already knew, but it was like a realization. For example, unlike steel, when you increase the strength of concrete, you increase its stiffness. And in a tall, slender building, one of your biggest concerns is the deflection of the building. So that became an added reason to use concrete with high strength concrete and make it more adaptable to tall buildings. The next realization was the understanding that what governs most of our tall buildings structurally is its vibration characteristics, specifically the accelerations you get on the top of the building. So you design this building, if you ignore that, the chairman of the board is sitting on the top of the building, and he finds himself very uncomfortable. You know, velocity is very easy, all right? But acceleration is the change in velocity. So it makes you very uncomfortable. So the realization that we had to design these buildings to make them comfortable, and acceleration is also, if you get too much acceleration, you can have a structural problem, okay? Led to more work with concrete because of certain reasons. One of them is that concrete gets stronger. Gets stiffer as it gets stronger. So you get a stiffer building. I already mentioned that affects the deflections. But the other interesting thing is, intrinsically, concrete has more damping than steel, twice as much. And what I mean by damping, okay, if I hit this, I won't hit it. If I hit this and you had your hand up there, you might feel a vibration. If it's a well-damped material, you may not feel that vibration. It slows down the vibration. With concrete, you get much more damping. In fact, the term is used percentage of critical damping. Concrete has about 2% critical damping, and steel has 1% critical damping. So that's why you see, if you study all these buildings, when you see a really tall building made of steel, there's a 95% chance it's got a tuned mass damper on the top. Some weight that's moving in the opposite direction.
Taipei 101, which is
Yes.
Thornton Tomasetti design,
Yes,
right?
exactly.
Steel, yeah.
That's steel. And we have this big, beautiful damper. In fact, people go up the elevators and they watch the damper. It's like a big fun thing. But typically with concrete, you can get away without using that damper. So all of these things add up to giving you more and more motivation to use concrete. Any questions on that part yet?
Why don't we have Tom, you could, why don't you just talk about Chicago and,
Sure, yeah.
and your limestone and all of those things that
Yeah.
we
Well,
discovered.
as a Chicagoan, I love it when New Yorkers acknowledge our city at all.
I've been there so many times, I have to.
But the Chicago story to me was one of both having brilliant people like Fazlur Khan and Bruce Graham who understood the potential for the material of the systems, but then having the industry, which happens to have, we are built on limestone in Chicago. It's down 100 feet below the clay, but it's there. And it's very good aggregate for concrete. It's stuff that you make gravel and things out of, but it works very well as aggregate. And the concrete industry in Chicago went hand in hand with the construction industry. So Material Service, this kind of legendary company in Chicago, worked with companies like McHugh, which built Marina City. Marina City is the first, as far as I know, the first use of fiberglass forms to create complex curved shape. But it's also one of the early high rises that Material Services contributed to.
Mention the Crown family.
The Crown family owned Material Services and went on to buy General Dynamics, among other things. But they came out of the concrete industry in Chicago. And Material Services just incrementally throughout the 60s, 70s, and 80s was able to produce these higher and higher strength concretes by literally just playing with the mix of the cake. And there was this nice kind of synergy where architects want to go taller, engineers are developing ways of taking advantage of the higher strength concrete. Material Services is finding ways to produce better and better mixes. That is kind of a unique, it took advantage, I think, of Chicago being a big small town where everyone in the industry still kind of knows each other, and certainly it was the case back then. But I was interested to hear you talk about that move from engineers specifying the concrete mix to kind of leaving it in the hands of suppliers, and whether that was in fact just a Chicago thing or was that industry-wide. Is the kind of recipe for concrete more and more throughout the late 20th century something that the industry is doing or something that engineers are pushing?
Well, as I recall it, the concept probably started in Chicago. Okay? Chicago had the best concrete, it really did. Okay? I'm making him happy again. But I think now, today, I can't even tell you how it is all around the world, okay? But I do know, for example, there are certain buildings that special things had to be done to get that a good concrete mix. Talking about the Kuala Lumpur, the technology was not there. You know, you couldn't dial 201 in New Jersey and say, get me some high-strength concrete, all right? And they built, and this has been done on other projects, they actually built a whole batching plant right at the site, okay? And then the concrete came from the batching plant to that. But I would say in general, we still now rely on the manufacturers because it's a specialty, okay? And if it's being done outside of the manufacturer, you're going to have a materials engineer involved as a special consultant because it definitely is a special thing. But also, if I can just add to that, we keep talking design. You actually have to construct these things to get them up there. So when people first started thinking about a concrete high-rise, they go, what are you, crazy? How could you ever get the concrete up there? So there's been a lot of advances in pumping technology. And one of the things that may have given us a little kick, when you go back and look at the differences between a 5,000 PSI concrete and maybe an 8,000 PSI concrete, it seemed that more often than not, the higher strength concretes have a little more fluid to them and they were easier to pump. Now, as you get into the 14,000 PSIs and above, or even 12,000, I would say you have to reevaluate that based on the details of the mix, and you'd have to really consult a particular manufacturer. But there was a lot of advantages there for concrete, and a lot of development in the pumping technology that allowed us to build these structures and be able to pump the concrete up that high.
Do you want to talk about the Portland Cement Association and whether it's the industry, but as a kind of knowledge base and sharing?
Yeah, I mean, the other thing is that the Portland Cement Institute recognized, I think, that steel had the kind of jump start, right? That steel had really standardized in the 1890s with Carnegie. You could order from Carnegie and know exactly the shape of the steel you were getting. You knew exactly the strength, exactly what, how it was going to perform. They would even do the engineering for you if you asked nicely. And concrete didn't have that. It was a local material, so it was kind of the Wild West in terms of what you got. Portland Cement Institute really worked hard at standardizing
in Skokie.
In Skokie, Illinois, right? So they were convenient to practitioners in Chicago. Another reason I think that it took off there. But to me, there are kind of two interesting parts to this, right? One is the concrete industry realizing that it had to develop its own set of rules, basically, to compete with steel, that you needed a reliable material. And then talking about Petronas, realizing that concrete is legitimately a global material because all you need to build in it really is a source of aggregate and sand and water. You can import the cement, right? That's the kind of smallest part of the mix. Whereas if you're building a building in steel, you need to import all of it to Malaysia. So I'm curious to hear your thoughts, your recollections about those two kind of moments where concrete became a kind of standardized material, and then also its kind of global spread, and how that was influenced by the kind of availability of aggregates in various places.
Well, very much influenced. I think when engineers first started doing a lot of projects overseas, especially in Asia, there was no steel, okay? Even if there was steel, there was no fabricator. The amount of work that goes into making every one of those members on the steel structure, the holes that have to be drilled, the connections that have to be made, none of that was there. You don't just get that all of a sudden. You need a whole industry that has to be there, okay? And it's similar with concrete. Often, depending on where you are, okay, you might be limited to a certain extent of what type of concrete you can use, okay? As Tom mentioned, because concrete has a lot of aggregates in it, okay? Think of them as little shells, all right? Okay? And if you're using lightweight concrete, they're kind of little shells with voids in them. And you're kind of stuck with what's in the neighborhood. It could become very expensive to ship that stuff, right? So there's a variety of things that come in. I mean, you don't do concrete buildings in Pittsburgh, Pennsylvania, when you have a big steel industry there, okay, and vice versa with other areas. So it's the availability of the materials that also affects your choices. Bring that to present day, okay, the availability of materials, right, is also influenced by green technology. For example, the carbon footprint of your project is going to be a lot bigger if you're ordering materials that require a heck of a lot of transportation to get those materials to your site, right? So these things come into our thinking these days also.
I'm going to interject here because one of the questions that Tom and I were asking about the whole spectrum from the 1880s to the present is why didn't concrete get organized as an industry, as an industrialized product, as a way of working, a predominant way of working? So, you know, we're architecture historians and architects and engineers, and we're telling this as a story of progress that's moving forward. But there's the story of stasis in the industry, and if I were an economist, I think I would, and I've studied industrial organization, is why was it so unorganized? Why didn't it happen in the first 60 years of this material? Because steel and reinforced concrete are born at the same time, in the same decade. So I don't think we have an answer. I don't know if there is an easy answer, but it's important to observe that concrete just didn't get up out of the ground in the same way that steel did. But at the same time, concrete was from the Lehigh Valley was building the Panama Canal. You know, it was in the Empire State Building.
Hoover
you know, and Hoover Dam, right? That went a ways. You know. So why didn't it happen? We have economists here who might be able to struggle with that question at some point.
Well, I'll just interject with that. One thing about concrete, there were small contractors that had their wheelbarrows, and they were able to get a hold of some cement and get a hold of some water and get a hold of some little rocks, and they can actually make their own mix by themselves. You never had that in steel. Steel had to develop a big industry that supported itself. Nobody can just make their own little steel beams in their backyard. So I think, you know, concrete came out of a more rural approach of people doing things by themselves, and it took a while before they had these organized industries. Okay. Also, the technology wasn't there. See, steel was always very strong. Steel was always very, very stiff. We have stronger and stiffer steels now, or at least stronger steels now than we used to. But we really had a great start. Very hard to make a weak steel. You can make a weak concrete.
Very easily.
But there were plenty of innovators in the early part of the century, where there's Ennebeek and the Royal Liver Building, which looks like it could have been a steel building, except it's made of concrete, and the Perret brothers and that architectural historians know so well from the textbooks of the early part of the 20th century in Paris. So there were innovators in different structural systems that actually did begin to get a foothold.
Yeah. Which could be part of the reason, right? That you mentioned Ennebeek and Ransom and a handful of others had patents on their systems. So if you wanted a 16-story concrete building in Cincinnati, you went to Ransom and said, we're going to use your system. And the Ransom company would say, great, we'll do the engineering, we'll ship you all the reinforcing bar, we'll even ship you the kind of concrete mix. And my guess is that while those patents were in force, it would have discouraged one of those guys with wheelbarrows, even if they had a better idea, from actually being able to develop it into a system. That the patents were probably innovation killers for a good few decades. They built some amazing buildings, but they also probably had a bit of a monopoly on concrete construction at a bigger scale.
So we're not going to sit here for too much longer, but I have one more question that might, be appropriate since Richard is here. But maybe you could preface it because one of the buildings in the back, the 2,000-foot tall towers, there are two of them in Chicago that didn't get built. The Miglin-Beitler Tower. Maybe you could tell that story as a Chicagoan a little bit about how they happened at this time to be designed, but then not built. And then Richard, who was part of the team designing the new structural system for that 2,000-foot tower. You can tell us, your story.
Well, the kind of macro story is that Chicago had an incredibly hot real estate market in the late 1980s, and the skyscraper is a machine for making the land pay. So the more stories you can stack up, the more money you make. But also, to your point about kind of branding, there was an idea. There's always been an idea in Chicago that we have the tallest buildings, or we should have the tallest buildings. And I think things like Petronas Towers, where Chicago loses the world's tallest, gave a little bit of an impulse to kind of see what we could do in the city. So those were all speculative, but they had developers behind them who thought they could make them pencil out. The problem was that there was a lot of other building that went on as well. And as a young SOM intern in the summer of 1990, I very well remember the day coming into work and seeing the Sun-Times newspaper headline, 6 downtown developments go on hold, and walking into the office and realizing that we were not going to be as busy as we thought we were. That summer was a very, very sudden crash, and it affected the Miglin-Beitler and a couple other of the really tall towers. I think 7 South Dearborn was either about the same time, or it was
almost 10 years after.
10 years after. So
the
that
Sky
was
Needle, yeah.
Yeah, so that was the 2001 recession. But
What was the question,
Well,
Carol?
what can you tell us about, I know it's your partner, the late Charlie Thornton, who was, I think, the principal structural engineer on that, on the Sky Needle project, which was designed by Caesar Pelli, but how was the office excited about this at the time? What do you recall?
I'm going to go back to something that one of our mentors, the original name of the firm was Lev Zetman Associates, and something he always said. Okay? He says, when you're trying to have a new or different material be used for a structural purpose, you can't just substitute it in the form of the material you were previously using. What's the best form for that material? Now, the story of the Miglin-Beitler, when you look at that, it's basically a shear wall kind of structure. And our studies led to that, not to have a frame, not to just have a core and then a frame around it, but to have shear walls that bring all the load down, and then it changes as you come down, which is similar to like Burj Khalifa, okay?
And Jeddah, yeah.
And Jeddah, which we're doing in Saudi Arabia, if it ever gets finished, okay? So I think that was the motivation of that project, is what's the best form so we can get this building that high and use all the good things about concrete. It's better damping, it's increasing stiffness as you increase the strength. They were the considerations at that time. In fact, I'd just like to interject something so everyone in the audience understands, if they're not involved with the engineering and architecture of these things, because we keep talking about the dynamics, all right? I think it's important to understand where the dynamics come from. And it's really very simple, okay? When the wind blows on something, it separates. Okay? And when it separates, you get these things we call eddies, and they're like a little vibration. And they're a little different frequency on one side than the other side. And that's what causes these vibrations. And what many of you may not realize, the major vibration or the major accelerations are happening perpendicular to the wall. perpendicular to the wind, not in the direction of the wind. It's because of that separation of, and that's what we're constantly battling in the dynamics of high rise. And
Which
that
is why
typically-
we have wind tunnel models in these
That's
two,
right,
yeah, in
always
the two
wind tunnel.
cases.
And the typical high rise, the wind forces will typically govern the overall design more so than the seismic forces because of the flexibility of these buildings. But that doesn't mean you still don't have to design certain things into that project to make it ductile enough so it can resist the kind of seismic forces that it would experience.
So by way of concluding, and feel free to chime in also, in the two words that Richard just used, shear wall, I in my simplicity like to emphasize wall,
Yeah.
right? And because this is gravity going down through a wall, not through a column, not through a frame, but as a wall. And if you ask concrete what it wants to be, one of it, we would always have this little tete-a-tete about it. I think that concrete would answer anything you want.
Right.
But when you ask the Romans, they would say a wall
Sure.
or a vault, but a solid,
Yeah.
right? And so and that was kind of the fundamental instigation for this inquiry about the role of concrete in the skyscraper and the ubiquity of it today.
Yeah, I agree with that. I think that's the lesson I've taken away for sure. I love that Zetlin quote, and I'm going to steal it because I think that this has been a really interesting exercise in the relationship between material and form. And we've spent as much time talking about the way concrete gets formed as how the structure works. So I think that's perfect note to end on. And I would just say thank you for the opportunity to play around with this stuff.
Thank you for
as long as
making it
we
all
have.
fun.
And Richard, it's just been a great honor to sit up here with you today and appreciate the input you've had as well.
Thank you, Carol. Thank you, Tom.
Thank you, Richard. Thank you.